Welcome back. Every single time you tweet or buy something online or even just search for something, you're creating data. And all of that data from billions of people is creating this massive digital deluge. It's a huge problem. So today, we're going to find out how a really clever technology called Hadoop managed to tame it.
I mean, this is really the fundamental question, isn't it? Just try to imagine a single file that is so enormous, so mind-bogglingly huge, that it just won't fit on the biggest hard drive you could possibly buy. So what do? How do you even store it? And let's say you could store it, how on earth could you possibly process it? This is the core challenge of big data.
So this problem got so big that industry analysts had to come up with a formal definition for it. And what they realized is that it's not just about the size, what they call volume. It's also about velocity. I mean, how fast is the data flooding in, and variety, because it's not all neat and tidy. It's text, images, sensor readings, you name it. Yeah, those first three V's are kind of the classic ones, but the model has grown a bit. We've added two more that are absolutely crucial. First is veracity, which basically means, can we even trust this data? Is it accurate? And then, probably the most important one, value. Because what's the point of collecting all this data if you can't get something useful out of it? So here's the real kicker. Our old tools, the ones that ran the world for decades, they just couldn't keep up. You take a traditional database, even one running on a super powerful server, and you throw this kind of load at it, and it just grinds to a halt. It literally breaks. The old way of doing things was completely busted, which meant we needed a totally new way of thinking.
So how do you store a file that's too big for any single computer? Well, the first part of the solution is this really clever storage system called the Hadoop Distributed File System, or HDFS for short.
And the idea behind it is, it's actually brilliantly simple. Instead of trying to build one gigantic, impossibly expensive supercomputer, you just take a whole bunch of cheap, ordinary computers, a cluster of them, and you use software to make them all work together, like they're one single massive file system.
So how does HDFS actually pull this off? Well, when a giant file comes in, HDFS acts like a digital wood chipper. It just chops the file into these big, uniform blocks, like say 64 megabytes each, and then it just scatters those blocks across all the different computers in the cluster. It's that simple.
Okay, but you might be thinking, what if one of those cheap computers fails? Does a piece of my file just vanish forever? Nope, not a chance. HDFS has this built-in safety net called replication. It automatically makes multiple copies of every single block and is smart enough to store them on different machines. So if one computer dies, there's always a backup copy ready to go.
Now, there are a couple of ways you can manage these copies. You could have a master-slave setup where one computer is the boss. It's in charge of all the writing. This is great for things like websites that get read way more than they get updated. Or you could go with a peer-to-peer system where every computer is an equal. It's a lot more decentralized.
Right, so this brings up this classic, really tricky problem in distributed systems. When you write new data, do you wait for it to be copied to all the replicas before you say, yep, it's saved? That gives you super strong consistency. But what if one machine is slow or offline? Your whole system has to wait. Or do you prioritize availability, responding right away, and just trusting that the copies will catch up later?
And this really highlights a huge trade-off between two completely different philosophies. Traditional databases, they live and die by something called ACID. They guarantee that every single transaction is perfect, atomic, consistent, the whole shebang, right now. But big data systems, they often prefer base, basically available, soft state, and eventual consistency. They're built to stay online no matter what, accepting that the data will sync up eventually.
Okay, so we figured out how to store this enormous file across hundreds of machines. Awesome. But now, how do we actually do anything with it? We can't move all that data back to one place. That would be insane. So instead, we take the work to the data using a programming model called MapReduce.
The best way to think about MapReduce is to picture a general commanding an army of ants. See, instead of one person trying to carry a giant picnic basket all by themselves, the general tells every single ant to grab just one crumb and process it right where they found it. It is a massively, massively parallel way to get a huge job done.
Let's make this really concrete with an example. Imagine we have a file that's a petabyte in size, just trillions of temperature readings from weather stations all over the world. Our mission, should we choose to accept it, is to find the average temperature for each and every day.
First up is the map phase. Each computer in our cluster looks only at the little chunks of data that it has stored locally. It reads through its piece of the file, and it maps it, creating these simple little pairs of data. In our case, it pulls out the key, which is the date, and the value, which is the temperature reading for that date.
Next up is the part that feels like magic, the shuffle and sort phase. The Hadoop framework automatically goes out and collects all of those little pairs from all the different computers, and then it groups them by their key. So all the temperature readings for January 1st end up in one big list, all the readings for January 2nd end up in another, and so on.
And finally, we have the reducer phase, a new set of workers. Called reducers, each grabs one of those lists. So one reducer gets the massive list for January 1st and calculates the average. Another reducer gets the list for January 2nd and does the same thing. They reduce those huge lists of numbers down to a single, simple, final answer. And that is how you process a petabyte of data in minutes instead of years.
So we can store and process these unbelievable amounts of data. But why? Who cares? What's the point? Well, the real payoff is in the quality of the insights and the decisions we can make. It's about climbing this ladder of understanding.
And this journey, this climb from just raw data to actual wisdom, it happens in 4 pretty distinct stages. With each step up the ladder, you get so much more value.
At the most basic level, the first step on the ladder, you have descriptive analytics. This is basically your rearview mirror. It just answers the question, what happened? But of course, knowing what happened isn't always enough, right? So diagnostic analytics digs a little deeper. It's all about finding out why it happened. Why did sales dip last quarter? Let's find out. Okay, now this is where it starts to get really powerful. Predictive analytics takes all of that past data and uses it to build models that can forecast what's probably going to happen next. We're moving from looking at the past to looking into the future. And then, at the very top of the ladder, this is the holy grail, prescriptive analytics. This doesn't just predict the future, it tells you what you should do about it to get the best possible outcome. You know, it's the difference between a weather forecast that says it's going to rain and one that actually tells you to bring an umbrella.
And that leaves us with this final, and I think, fascinating question. Technologies like Hadoop, they've given us this unprecedented power to analyze the past at a scale we never could have imagined. But as we get better and better at this, how much of the future can we really predict? And maybe more importantly, what does that mean for all of us? Something to think about. Until next time.